Today we will be discussing on chapter number 7, fluid dynamics. So we will be covering especially on Bernoulli and energy equations. Okay, so under this chapter we will be having three subtopics, which is fluid flow rate, okay, continuity equation, and Bernoulli's theorem. So continuity equation together with Bernoulli's theorem can be used to find unknown parameters related to fluid dynamics. So like pressure, velocity, or different height. So all these values can be uh, obtained from the continuity equation together with Bernoulli's theorem. And what we need to understand that it must fulfill certain conditions before we can use it together. So everything we will be covering in this. 7.1, conservation of mass. So what is conservation of mass? So let's say we see this example. So 2 kilograms of hydrogen. So you mix it with 16 kilograms of oxygen. So the yield will be 18 kilograms of hydrogen, hydrogen oxide or H2O. Okay, so we know this is the conservation of mass. So energy cannot be created or destroyed, it only can change form. So similarly here the mass is conserved. But when we see closed system, so closed system, the conservation of mass principle is implicitly used by requiring that the mass of the system remain constant during a process. So what it says, so for closed system we know no mass coming in or going out of the system. So no mass transfer. So the mass will be constant for closed system. But for control volume or the open system, so mass can cross the boundary. So it can come in or go out. So we need to keep track the amount of mass entering and leaving the control volume. Okay, it will be used for our analysis. Okay, so when we say flow rate or mass moving in and out, so that's a fluid dynamic because the mass uh, in our case is fluid. Fluid, it has a mass. So it has a kg, so or weight. So the mass will have a flow rate. Okay, so that is what we call as a mass flow rate, or we always write it as m dot. Okay, so what is mass flow rate? The amount of mass flowing through a cross section per unit time. So in one particular second or minute, how much mass is passing by one area of cross section. Okay, so that is what we call as a mass flow rate. Okay, so let's say this is your control surface, okay, or the boundary. So that let's say this is the area, cross section area that you want to investigate. So how much mass is going out of this area? So that is what we want to calculate. So it can have different angles. So depends on what you want to find. You know, whether it's a angle or the, the how to say, well, the resultant velocity. So all that we can estimate. Okay, so this is the formula to calculate. So we will see about this later. Okay, so mass and volume flow rates. Okay, so the formula that is written here. So we know m dot equals to rho VA. This is what we studied in our previous lectures. But in this case, so what is the symbol differential? So we can write it as a similar to S. Okay, so S and D always will be used to indicate a small changes. Okay, so both are indicating a small changes, but if you see the note here, both differential and D are used to indicate differential quantities, but differential is typically used for quantities that are path function and have inexact differential. So meaning is a path function is moving from one point to another point, but in between you can have different values. So that is what we call as a path function and inexact differential. It's not constant throughout the path. While D is used for quantities that are point function and F exact differential. So D we will take not based on part, it will be based on points. So different point, it will have an exact value. So we can use it to calculate the mass and volume flow rate. So flow rates, we have a few types of flow rate. So earlier we have seen the mass flow rate. So we also have a volume flow rate, which we will discuss in a while. Okay, so this is some of the derivation. So how you can get the value. Okay, so I'm not really discussing on the derivation, so you can go through by yourself. The steps are given. Okay, the mass flow rate through the entire cross-section area of a pipe or duct is mass flow rate. Okay, this is the derivation for this formula. Okay, so how we can get this formula? So the steps are given. Okay, so average velocity. So this is something important. Okay, important when we consider, because when we have a movement of fluid in a pipe, it will have a different velocity at different points. So why here closer to the boundaries or closer to the pipe or wall, so the velocity will be lesser, is because of no slip condition. So no slip condition, we have discussed before this. So that's the place where frictions will be applied, because the fluid will be in contact with the surface of the wall of the pipe. So it will cause a no slip condition. But at the middle part, so we have a lesser friction or almost no friction, so the fluid can move in a better velocity. So in order for you to do analysis, so we cannot like investigate separately. We need to take average of all these points. So let's say here maybe 10 meter per second, here 12 meter per second, here 15 meter per second. So all these line will have a different velocity. So you need to add up and divide uh, by the uh, number of sample in order for you to get the average velocity, or you can use this formula. Okay, mass flow rate for incompressible flow. Okay, so this is the formula that we have seen here. So m dot, okay, m dot is mass flow rate equals to rho v average, velocity average, and cross sectional area. Or we can write it like this. Okay, so earlier we have seen on mass flow rate. So now volume flow rate. So the symbol is v dot. Okay, so similar like the mass flow rate definition, the volume flow rate is the volume of the fluid flowing through a cross section per unit time. So meaning in 1 second or 1 minute, how much volume of that particular fluid is passing through that cross section. So, so let's say this is the volume. This is the area that you want to investigate. Okay, so you have a cross section here. So you have a volume here. So how much volume is passing through this cross section in 1 second or 1 minute? So depends. Okay, so this is the formula that we can use. V dot equals to average velocity times weight cross section area. So VAC. Okay, so the relation between mass and volume flow rate. Okay, m dot equals to rho V dot, or V dot per V. So here, this is volume flow rate. This is the velocity. Okay, conservation of mass 7.12. Okay, conservation of mass. What is conservation of mass? So to easily put, so this is the formula. So total mass entering the control volume during a time taken minus total mass leaving. So mass entering minus mass leaving the control volume. Okay, so that is the net change of mass within the control volume during the changes of time. Okay, or if you can put it in the uh, formula, So M in minus M out. So M is mass, M in minus M out. So both in kilogram equals to changes of mass or the net change of mass. Okay, the change in mass of the control volume in rate. So rate we know it is m dot. Okay, so m dot in minus m dot out equals to changes of mass of control volume over time. We consider a control volume of arbitrary shape. So let's say the control volume is not a fixed shape. So we just take a area that you want to investigate, and you can divide it into two lines, so which is 90 degrees to each other, or with that with the certain angle theta. Okay, so the mass of a differential volume within the control volume. So dm equals to rho dv. This is the formula that we have seen earlier. Okay, so total mass within the CV we can find by integrating this formula, and the net change of mass within the CV, so we can find using the formula. Okay, the cases with no mass crossing the closed survey or closed system. So this part, so dm CV over dt becomes 0 because no mass is exchanging. It's all these some of the formulas for you to understand from where these formulas are derived and how it's derived, just for your understanding. We consider mass flow into or out of the control volume through a differential area. So earlier we have seen, so mass is entering or exiting area. Uh, so you can divide it into two. Okay, so if we put in 2D, so it will be like this. So this is the dA. So this is n and this is v. So both are vectors with certain angle of deviation. An is outward unit vector of dA, normal to dA. So normal to dA meaning, so this is dA. So normal means is 90 degrees to dA, and v is a flow velocity related to a fixed coordinate system. So this is a flow velocity at a certain. So based on mathematics, so we can calculate. So Vn equals to V cos theta. So V cos theta or V vector times with n vector. So it's a product of both these vectors. Okay, so if you recall the formula that we have created earlier. So we know this is the formula. So here from here we can derive. So we just substitute this into this formula. Okay, because we know Vn equals to, so either V cos theta or Vn, V product of vectors V and n. So we can just substitute in this formula, replacing this Vn. So we will get this formula. And for net mass flow rate, so we also can replace it by using this formula, and at the end we will get this. So depends in the question in your exam. So let's say the information of theta is given or the information of v is given. So you can use only this formula to calculate the differential mass flow rate. So similarly for the other two. So if the value of vector v is given and n is given, so you only can select this. Okay, so we are in this lecture note, we are just showing all the available formulas for you to consider. Okay, so if we recall the mass, the changes in mass of the control volume in rate form, so we know that m dot in minus m dot out equals to dmcv over dt. So this from the previous slides. Okay, so we bring this to the left hand side, so equating it to 0, so we get like this. So this is some derivation, and we also can recall from the previous slides about these two formulas. So we replace it into this formula. So these two information we replace it here. So we will get at the end this derivation. Okay, so now we are actually looking at how we develop the continuity equation and also the Bernoulli's equation. So these are some of the steps to derivation. Okay, so the time rate of change of mass within the control volume plus the net mass flow rate through the control volume is equals to 0. So this is for this part. Okay, so if you continue to derive, so you can even break it into few steps. Okay, so I'm not really going into this derivation. So I think it's a bit straightforward. If you look at the lecture note, you can understand the steps. So it's a basic mathematics. Okay, so let's say the control surface at an angle to the flow. So the area that you are investigating, if it's in the angle, then you need to consider the data. Okay, so um, if it's a normal to or in parallel to the direction of the flow, then the formula will be much simpler for you to consider. Okay, so this is from the derivation. So we know that this is the angle going up. So going out. So Vn is V cos theta. Okay, so we can just substitute it with m out and minus m in. So at the end you will get the formula like this. Okay, the summation of m entering minus the summation of m going out of the control volume equals to changes in the system. Okay, so mass balance for steady flow process. Okay, during a steady flow process, the total amount of mass contained within the control volume does not change with time. Okay, so steady flow. So mass changes will be constant. When dealing with steady flow processes, the focus is the amount of mass flowing per unit time, which is the mass flow. Okay, so this is for steady flow process. So steady flow process, so it will be much easier to calculate. So because we know the the, the control volume does not change, that the amount of mass contained within the control volume will not change. Okay, so from the formula we derived earlier, so we can come up with a few other derivations. Okay, so let's say since mcv is constant, so this part will become 0. So at the end, if we rearrange, we will get, so the mass flow rate entering the system equals to mass flow rate exiting the system, similar like here. So 2 kg ms1 m dot m.1, so m.2 is 3 kg, so you mix it, so you'll get 5 kg per second. So that is fulfilling this formula. For single string, only one inlet and one outlet. The inlet state and the outlet state are denoted by the subscript 1 and 2 respectively. We know. So 1 is input, 2 normally will be output. Okay, so it will be mentioning in the figures or the question. Okay, so mass flow rate for single string steady flow. So we know based on this. So since the summation is multiple, so if let's say it's only for single string, so you only take one. So m1 dot equals to m2 dot. Okay, so this is your continuity equation. Rho 1 v1 a1 equals to rho 2 v2. Okay, so special case. So let's say it's an incompressible flow. So incompressible flow, so meaning there's no changes. So you will get the similar formula. Okay, so incompressible, no changes in the density, so you can cancel it out. So VA is equals to volume flow rate. So from here we can get this formula. The summation of volume flow rate entering equals to the summation of volume flow rate exiting the system. Okay, so mass flow rate for single stream. Okay, so this there's a mistake here. So it's not mass or volume flow rate. Volume flow rate for single stream steady incompressible flow. So V1 dot equals to V2 dot. So this uh, you can have it like V1 A1 equals to V2 A2. So this is a continuity equation. Okay, so you can check something like this. Okay, so single entry, single exit. Easier for us to calculate using the equation of continuity. Okay, so now we enter to the Bernoulli's equation. So Bernoulli's equation is an approximate relation between pressure, velocity, and elevation. So pressure we know is P. So velocity normally will be V, and elevation normally will be Z. So if you see this formula, so it will have P, V, and Z. So which we can combine. So we will see later. So what are the parts of Bernoulli's equation, and we also will show some derivation for you to understand. But I'm not going to discuss on the derivation, but it's just you can just follow how this formula is derived. Okay, so you can see. And one important thing about Bernoulli's equation, it is valid in a region of steady incompressible flow where net frictional forces are negligible. So meaning this Bernoulli's equation cannot be used in all the situation, because if there's a lot of friction, there's a lot of vorticity, a lot of changes, then you cannot apply Bernoulli's equation because it will keep on changing. You can apply Bernoulli's equation, but you need to take point by point. So you cannot take for the whole part. So it will be inaccurate then. Okay, so it will be really important, especially for engineers, to estimate, at least have a rough idea uh, of the pressure, velocity, and elevation at the region of steady and incompressible flow, for us to estimate the output of the other uh, not steady compressible flow situation. Okay, so this is the formula of Bernoulli. The Bernoulli, or we call it as a Bernoulli's equation. So P over rho, okay, pressure over rho plus velocity square over 2 plus gz, g is gravity, equals to constant. So let's say you have 2 points, and then you can have this equation. So P1 is zero point 0.1, so 2 is 0.2. So 0.1, so the same equation here for 0.1 equals to the same equation for 0.2. So it will be steady. So the value will be the same. Okay. So let's say the question gave p, give rho, give z for both condition, but v is not given. So the unknown parameters you can find. Okay, you can find using the Bernoulli's equation. Okay, Bernoulli's approximation is typically useful in flow region outside of boundary layers and wakes, where the fluid motion is governed by the combined effect of pressure and gravity forces. Okay, so from this picture, we can see where Bernoulli's equations are valid and where Bernoulli's equations are not valid. So let's say you have a flow region, so or we call it as a wake. So this area, so what will happen? So after some time, suddenly it stops. Okay, this flow suddenly stop, because suddenly have friction. So the Bernoulli's equation cannot be used in this region. Okay, but along this streamline, so let's say it's a streamline. So year point 1, year point 2. So you can take the values. You can take the values and you can use this formula to find. Okay. So these are the regions that Bernoulli's equation will be valid. So later I will tell you what are the other points that make Bernoulli's equation valid. Okay, so this is one of the points. Okay, so acceleration of a fluid particle. Okay, the motion of a particle and the path it follows are described by the velocity vector as a function of time and space coordinates and the initial position of the particle. When the flow is steady, no changes with time at the specific location. All particles that passes through the same point follows the same path, which is the streamline, and the velocity vectors remain tangent to the path at every point. So you can see here. So if the flow is coming from here, connect to the same point and going at the same point, we call this a streamline. Okay, streamline. So at the same streamline, so the values will be or will be the same. Values will be the same. So the values of velocity, the values of pressure, and acceleration will be the same. Okay, the motion of a particle in terms of its distance s along the streamline together with the radius of curvature around the streamline. So the radius is, so let's say is a pipe. So it will have a radius, and the motion of particle in the pipe will be the same, and it will move here to a distance of s. Okay. So the speed of particle is related to the distance. So this so velocity we know from physics, v equals to ds over dt. So s is the distance covered over time. So that is velocity, which may vary along the streamline. Okay, so different streamline can have different velocity, but same streamline should have the same values. Okay, so let's say you do a two-dimensional. So this is a streamline, the green color. So it will go straight. So this one streamline. But if you take a two-dimensional flow, so the two-dimensional means two angles. Okay, so like here you can see the angle um, normal to the flow, the streamline. So which is n, and um, the the angle tangential to the movement of the fluid, so is s. Okay, so that's the two-dimensional flow. The acceleration can be decomposed into two components. Streamwise acceleration, so this is as, okay, along, and normal acceleration an, the direction normal to the streamline. During steady flow, a fluid may not accelerate in time at a fixed point, but it may accelerate in space. So you see what is this. Okay, so let's say take a velocity v of a fluid particle to a function of s and t. Okay, so v st, so this is a function of s and t. Take the total differential of v st and dividing both sides by dt. Okay, um, so we know, so for s is a dv over ds. Okay, so this is a differential. Um, so dv over s, because you are taking functions of s and t, so you are dividing v by s and also d by t. So differential v over s, differential s times with ds plus differential v over dt times with dt. So you are dividing both sides by the ills of dt. Okay, so you are dividing this by dt. Okay, so you will get this formula. Okay, so this is from uh, this derivation. So you will get dv. Then once you divide by dt, so you can divide ds by dt and dt by dt. So once you solve it, what you will get? So dt over dt, you will get 1. Okay, so at the end, you will get this formula. Okay, no need to cancel this side. So you only cancel the right hand side. So after some time, you will get this value. So dv over dt, we know is an acceleration. Okay. So for steady flow, the differential v over differential t, so differential v over differential t will become 0. So after some time, so we know, so this is the only component that will be available. Is acceleration in the s direction. So as equals to dv over dt equals to differential v over differential s times with ds over dt. So ds over dt we know is a velocity. So velocity, so which is v, then we can get this formula. So this is the derivation of acceleration in s direction. As equals to v dv over ds. Okay, so the acceleration in the n direction become, so it will become 0. So because um, the radius will become, so the radius will be the same, velocity will become 0. So it will become 0 for the whole thing. Only as will have value. Okay, so using this, how we can derive the Bernoulli's equation. So Bernoulli's equation derivation, I'm not really going deep into, because the steps are given, so you can just follow and try to understand how the formula is derived, but I will try to explain some of the important points. Okay, so the derivation of Bernoulli's equation. So consider the motion of the fluid particle in a flow field, steady flow. So let's say the fluid is moving in a steady flow. So we can apply the Newton's second law. Uh, Newton's second law is F equals to ma. Okay, so we can, so the summation of force in the direction of S equals to MAS. AS is this part. In region of flow where Net frictional force are negligible. There's no pump or turbine, and there is no heat transfer on the streamline. The significant forces acting in the S directions are the pressure acting in both sides and the component of the weight of the particle in the S direction. So let's say the movement is this way. So you put it in a Z X graph. So Z is the elevation, X is the distance. So it will move to in the streamline steady flow. Okay, so this is the area that we want to investigate. So let's say this is ds. So we will have one force P applying on the dA, so PdA, and we will have a different opposite the opposite uh, force from the opposite direction. So since it's higher, the point here is lower than this point. So here P dP. So meaning the pressure will not be the same like this. So pressure will be higher. So P dP. So it will be opposing the movement, and you also will have the effect of gravity, which will produce a weight. Okay, so these are the things that will be. So if we change it into a two-dimensional picture, so it will be like this. So there are two force. So this is the dA, the area that is entering. F equals to P dA. P dA. So here the force will be, so F equals to so this is the changes how this part, the opposite part is then derived. So from this side it will be F P dA. So F equals to P plus dP times with dA. So that's the derivation, and you will also have a weight. You'll have a sine component and also cos component, and in between will be the resultant weight. Okay, so based on this, so we know, so you will have, we just take along the streamline. So this side, so PdA will go uh, towards forward, but opposite you'll have another pressure or another force, and you also have a force in uh, sine component. So that's why you have like this. Okay, so based on this, so you can use this formula, F equals to MAS. So AS we know, V dV over ds. Sorry, not dV. So this is a differential sign. So please correct in the previous slide. Okay, so V differential V over differential S. Okay, so it's not dV. So I think previous slide it mentioned dV. Okay, so here you can just substitute the values. Okay, force we know. So there are two types of force. PdA. So you need to minus because it's opposite direction. So we consider going upward is positive, going downward is negative. So PdA minus P plus dP dA minus W sin theta equals to, so M. So AS is V. So here is a mistake also. It changes in V over differential V over differential S. Okay, but since it's only one component, you can use it dV over ds, but make sure you define it properly. Okay, so what you are using. So in this case, I just maintain this. Okay, so since only one component is a differential. Okay, so after you solve, at the end you will get this formula. Okay, so we know the mass of the fluid particle is given, m equals to rho v. V is the volume, or we can take rho dA ds. All these are related to this. Here the weight of the particle is given as W equals to mg. So the calculation for weight, the formula for weight. So mg is, so m we know, rho dA ds, g is g. So you get this formula. So you use the trigonometric. So sine theta is dz over ds. So you are using this trigonometric. So dz over ds. So you already got all this information. So you substitute in the formula from the previous slide. So you try to substitute w and sine theta. So w is rho g dA ds here times weight. Sine theta is dz over ds. So you solve it. So here m, so you replace it with this. So all these components you already got almost the same. So either you have p, either g, rho, or a, or z. Okay, so you already got all the same thing. So here you can cancel dA, you can cancel because it's the same component. So ds, and ds also you can cancel. So here you can cancel with this. This one you can cancel with this. So at the end you'll get this. So you rearrange equating it to 0. So you will get the formula like this. So this is the derivation for Bernoulli's equation for your example. So once you get this, so you divide by rho. If you want to remove this 2 rho, so you get d p rho plus v dv plus g dz equals to 0. So we know v dv equals to half d v square. Okay, so dv square. So this part is for this. So we know we just replace it with this. So you take this and put here. So we will get this formula. So at the end, so considering the control volume, so you integrate, so you will get 0 will become constant, and all these components will become. So at the end, along a streamline, you can use this. So this is the derived Bernoulli's equation. Okay, so steps are given, so you just go through the steps so that you can understand better. In the case of incompressible flow, so this differential meaning, so it's changing along the way. But in the case of incompressible flow, so there are no changes. There are no changes. It will almost remain the same. So you can get this formula. So P over rho plus V square over 2 plus Jz equals to constant along a string. So don't worry, I will not ask you to derive all this. So but you need to understand, because it's a part of syllabus for you to understand how all these things are bringing to the derivation. So let's say there's a common question. So maybe not a derivation question, but um, let's say I ask based on your understanding how Bernoulli's equation is derived. So you need to tell. So what are the examples that I have given earlier? So the projection in the z x graph, and how the acceleration play an important role. So maybe I can ask that kind of question instead of a mathematical derivation. The mathematical derivation I won't ask. Okay, so between any 2 points on the same streamline, so you will have this value. So this is the Bernoulli's equation that we will use for calculations. Okay, so the Bernoulli's equation can be divided into 3 parts. So the first part is the flow energy. So there are 3 types of energy associated with Bernoulli's equation. Okay, so the first part is flow energy. So pressure over density. Yes, that is what we call as a flow energy. Then we have a kinetic energy. So kinetic energy we know of mv square. So mass is cancelled. So v square over 2 is kinetic energy because it's related to velocity. So flow energy related to pressure. So kinetic energy related to velocity, and Gz equal to is related to potential energy because over elevation. Gravity over elevation is potential energy. So all these three, so flow energy, kinetic energy, and potential energy together, we call it as a mechanical energy balance. Okay, so what is mechanical energy balance? The sum of the kinetic, potential, and flow energies of the fluid particles is constant along the streamline during the steady flow when compressibility and frictional effect are invisible. So mechanical energy is the combination sum of all these three, and for Bernoulli's equation, so you can use it because the steady flow when compressibility and frictional effect are negligible. So if the condition met, so you can use this equation to estimate. If force balance across streamline, force balance in the direction and now and normal to the streamline is the following relation applicable across the streamline for steady incompressible flow. Okay, so if if the this the equation, so if let's say the pressure A more than pressure B because it's a different streamline, so the values can be different. So you can still use this to estimate. Okay, so the flow along the straight line R uh, R is approximate is reaching infinity. So R is the Reynolds number. Okay, the Reynolds number you can get it the value from the calculator. So when it is infinity, so it will become this component, the kinetic component will become 0. Then you will get this formula. So you rearrange it, you will get this for you to find the pressure at one particular point. So the variation of pressure with elevation is steady incompressible flow along a straight line. In an inviscid region of the flow is the same as at the stationary flow. So let's say you are taking in a steady incompressible flow, a straight line. So over you want to relate it with elevation. So in point A to B, so B we know in stationary fluid. So A is at the free surface, so is having a atmospheric pressure. But B is in the depth, so we know so P plus rho GH. Okay, so the height is affecting. So PB pressure at B will be more than pressure at A. So similarly here, so the pressure at D will be higher than C. So it can be related to stationary. So that's why here PB minus PA for this equals to PD minus PC for this. Okay. So how we want to estimate for unsteady compressible flow? So Bernoulli's equation we still can use, okay, for unsteady compressible flow, but you cannot use it as flexible as for steady flow. Okay. You need to, because integration meaning, so different point will have a different values, so you need to integrate it. So if you integrate it, so you can also estimate for unsteady compressible flow. Okay, so that's one thing. Okay, so 7.2.5 static, dynamic, and stagnation pressure. Okay, so this is related to the Bernoulli's equation. So we know it's divided into three parts. So how we can relate the pressures? Okay, pressures uh, for this Bernoulli's equation. So the kinetic and potential energies of the fluid can be converted to flow energy, and vice versa, during the flow, causing the pressure to change. Okay, so we have this Bernoulli's equation. So let's say you are times this formula with density rho. So you will get this formula P plus rho V square over 2 plus rho GZ equals to constant. So this is the formula that you will get when you times this with rho. So we can divide it into three parts. So P is static pressure. Static pressure is a pressure that is accurate. So that's why it's only value P. So no other things. So we call it as a static pressure. The second part, so rho V square over 2, we call it as a dynamic pressure, and rho GZ. Rho GZ, I think you still remember the one that we use for static or hydrostatic pressure. So it is representing the hydrostatic pressure. So we can divide it into three by just times with rho. So all these things, static pressure plus with dynamic pressure plus hydrostatic pressure, we call it as a total pressure. So static pressure represents the actual thermodynamic pressure of the fluid, so which you can use any device to measure. So the value that you get from the device or pressure gauge, so that we call it as a static pressure. So dynamic pressure represents a pressure rise during the fluid in motion is brought to a stop is entropically. So if dynamic pressure is the pressure at the movement, suddenly you stop it. So what is the pressure? So that is what we call it as a dynamic pressure. So pressure in the movement. And hydrostatic pressure is not pressure in the real sense since its value depends on the reference level selected. It accounts for the elevation effect that is fluid weight on pressure. So hydrostatic pressure, I think you understood from static. So different level, so different height from the free surface, so we'll have a different. So it go deeper, so the hydrostatic pressure will be higher. So that's why you say it depends on the reference level selected. A sum of static and dynamic pressure is called the stagnation pressure. So we know, so we have three components. So if you just plus static pressure and dynamic pressure, we call it as a stagnation pressure. So, add up these two, it is called a stagnation pressure. The stagnation pressure represents the pressure at the point where fluid is brought to a completely stop centripetally. So because both static pressure and dynamic pressure, when you measure, you need to stop the flow. You need to stop the flow and you need to measure. So you can call it as a stagnation pressure. Stagnation means no movement, no changes. So you can take this value. So like this, so you can see. So you have a piezometer to calculate the value of P, and you can have a pitot tube. So this is the stagnation point. So the point where you measure P, P is here, and you measure the changes. So you can measure both the static pressure and dynamic pressure at this point, which we call as a stagnation point. So that's why even the aircraft or the submarines or boat, we will have this pitot tube and also piezometer to measure. Okay. So stagnation pressure. So this is the formula that we can get from the Bernoulli's equation. So once you rearrange at the end, velocity can be calculated by square root of 2 stagnation pressure minus pressure over rho. So you can get the velocity at this point. Okay, so earlier I've said there are some limitations related to Bernoulli's equation. So what are the limitations? Okay, so it must be a steady flow. So Bernoulli's equation is applicable to steady flow. Even though unsteady flow you can apply, but you need to make a lot of changes. But this Bernoulli's equation is used for steady flow and must not have a friction. Every flow involves some friction no matter how small, and frictional effect may not be negligible. So if the frictional effect can be negligible, and then you can use Bernoulli's equation. Okay, no shaft work. The Bernoulli's equation is not applicable in a flow section that involves a pump, turbine, fan, or any other machine or impeller, since such devices destroy the streamlines and carry out energy interaction with the fluid particles. When this device exists, the energy equation should be used instead. So, no shaft work. Shaft work meaning some work is done uh, to add up energy to the system, like pump. So normal flow. That's why in the house we use a water pump to increase the water pressure. So let's say your house the pressure is low. Your father go and or mother go and buy a pump, fix it, connect the initial tube to the pump. So the pump will help you to increase the energy in the flow. So turbine is the same. So it will convert it into a work. We also have fan. So why when you feel hot you on your fan because it will increase the airflow and give you a cooling effect. Okay, so all this will destroy the streamlines and you will have an energy interaction with the system that you want to investigate. So you shouldn't have any shuffle. Okay, so incompressible flow. So make sure the Bernoulli's equation only apply in an incompressible flow. So because you want to take into consideration the density. Okay, density is taken constant in the derivation of the Bernoulli's equation. The flow is incompressible for liquids and also by gases at a Mach number less than about 0.3. So if the Mach number you calculate less than 0.3, we can consider it as an incompressible flow. And where since it's involved a density, so make sure it's incompressible and no heat transfer. Okay, so the density of the gas is inversely proportional to the temperature, and thus the Bernoulli's equation should not be used for flow section that involves significant temperature change, such as heating and cooling section. So you shouldn't have a heat transfer to the system because when you have heat transfer, so the molecules or particles in the fluid will start to move vigorously, so it will affect the streamline. So whatever things that can destroy the streamline and have an energy interaction with the system should be avoided. Okay, so all these 5 points are the limitations of the Bernoulli's equation. So it's a common question in exam. Okay, so explain the limitations of Bernoulli's equation. So if that kind of questions are asked, so you must explain based on these 5 points. Oh, sorry, you have one more. Okay, flow along a streamline. So strictly speaking, the Bernoulli's equation is applicable along a streamline. However, when a region of a flow is irrotational and there is negligibly small vorticity in the flow fluid, the Bernoulli's equation become applicable across the streamline as well. So, so make sure the flow along the streamline you have a very small vorticity because vorticity cannot be avoided. So vorticity means a rotation in the flow. So there's a slight turbulence in the flow. So it's negligible. Then you can take into consideration. Okay, so the cases where Bernoulli's equations are invalid. So you can see sudden expansion. So if flow suddenly the area or the volume increases, so you can use a Bernoulli's equation. The narrow long tube, so different part, so the velocity might changes. So you cannot use a fan. Increase the energy, shaft work cannot be used. Heating section, so heat is transfer cannot be used. Flow through a valve, the valve used to control the flow. So you cannot use a valve unless the valve is open fully. So no effect to the flow, then you can use. Okay, so a wake you can use. We have seen earlier, sudden stop, sudden changes, sudden friction. You cannot use. Okay, so Bernoulli's equation will be invalid in all these cases. Okay, so hydraulic grade line, okay, HGL and energy grade line. So there are two types of line. So we call it as a grade line. So engineers will use to estimate the changes of energy, energy in a system. Okay, so we know, so this is the mechanical energy, and if let's say you times this formula, so this is the Bernoulli's equation. So this equation you times with 1 over g, 1 over g, so you will get this formula. Okay, so 1 over g, so the first component p over rho g plus v square over 2g. So here the g will be cancelled. So 1 over g times with 1 over g. So you will get h. H is the constant, okay, that will be used to calculate this HGL and EGL. Okay, so from this point, so again we can get three components. Okay, so earlier we times with density, then you can find different kind of pressures. Here you go times with 1 over g, and you can get another thing called as a 8. Okay, 8. So the first one is pressure 8 because it's related to pressure. Second one we call it as a velocity 8 is related to velocity, and the third part we call it as a elevation because it's related to height, different height. So there are three things: pressure 8, velocity 8, and elevation 8. All these three combined we call it as a total 8. Okay, so the pressure 8 is related to the static pressure. Velocity 8 is related to velocity. Okay, so velocity, and elevation is related to potential energy. Okay, so potential energy or the height of the system. So again the same formula. Okay, so how we can use this formula to calculate the HGL and EGL. So HGL is, so you have a reference plane, so which is Z equals to 0. So HGL is the first two sorry, the pressure 8 plus with elevation 8. Okay, so P plus rho uh, P over rho G plus Z. Okay, so you are taking pressure 8, the first part, and the third part. So you mix it, you will get HGL, hydraulic grade line. Okay, so hydraulic grade line is, so from reference plane until the first point. Okay, so let's say you have a system. Yeah, let's say it's like a dam. Suddenly you have a diffuser and also a pipe going to another point. So you can have uh, uh, flow checkers here. Okay, so like how we have earlier. Okay, so you can estimate. Okay, so from year to year is HGL, and from year from the reference plane to the top. So how you can get, you take the total 8. So all these three you plus, you will get your EGL. Okay. So based on this, so at the different point, so you can plot a graph. Okay, so the top part, the full line is EGL, and the dotted line is EGL. So you can get a graph from this point to this point. Okay, so the differences between HGL and EGL is dynamic heat, because here you are not mixing with V square over 2G. So that's the difference here. Okay, so for stationary bodies such as a reservoir or lake, so we know this is like a reservoir, is a uh, stationary unit. Okay, so the starting point, it will be at the free surface. Okay, so at this point, uh, the pressure will be cancelled, velocity also cancelled because it's a stationary point. So no pressure, because it's atmospheric pressure, so you cancel this. So EGL and HGL, so both these components are cancelled, only left Z. Okay, so that's why both are having same point. This point is just the elevation or the height, which is involved. Okay, so the EGL is always a distance, V square over 2G above the HGL. These two curves approach each other as a velocity decrease. So as the velocity keep on decreasing, it will get closer. So based on this formula, if velocity decrease, it will get closer. Okay, like here. And they diverge as the velocity increase. So oppositely, if the velocity increase, so it will become bigger. So or vice versa. Okay, so in an idealized Bernoulli type flow, EGL is horizontal and its height remain constant. Okay, so if you have a idealized Bernoulli type flow, so which you make EGL constant, then or EGL will become horizontal and HGL will differ. So now we have a computer to estimate this kind of estimation. So which you only want to investigate HGL, then you can plot on EGL as a straight line horizontal to reference level, and you only plot HGL. Okay, so for open channel flow, so open channel we know is like a duct, so where is only F, it will have both, so only partially filled with fluid. Above is the open air, then we call it as open channel flow. So if you don't know what is open channel flow, refer to the previous lecture notes. Okay, HGL coincide with the free surface of the liquid, and the EGL is a distance, V square over 2G above the free surface. Okay, so this is because open channel flow, it will have both fluid and also free surface. So you need to take the value of HGL based on the free surface. Okay, so earlier we have seen at this point. Now at the exit point. So exit point, what will happen? So at the pipe exit, the pressure 8 is 0. Okay, pressure 8 is 0 because it's connecting to the atmospheric pressure. So atmospheric pressure here and atmospheric pressure here will be the same. So it will pressure 8 will become 0, and HGL coincide with the pipe outlet. It will reach, so HGL will be atmospheric pressure, or in this case will become 0, And the only formula that will be available, or the value will be available, is v square over 2g, which is the EGL. It's a mechanical energy loss due to frictional effect. So that's why you see the graph is going down. Is from up is going down due to frictional effect, or more accurately is the conservation of thermal energy. So the energy loss and it converted into it. Okay, so the slope is a measure of the heat loss in the pipe. So even engineers can estimate the gradient of this graph to calculate the heat loss. So we call it as a heat loss in a pipe. Okay, so we try to reduce. They try to improve the pipe in order to have a lesser heat loss. A component that generates significant frictional effect, such as a valve, cause a sudden drop in both EGL and HGL at the location. Okay, so let's say you are suddenly using a pump in a system, so you can see the EGL and HGL will suddenly increase. So like here you can see suddenly there's a differences in the size, so you can see it increases. Then after some time it will drop. Okay, so if you have turbine, so energy will loss from the system, so you can see sudden drop. Okay, pump will increase the energy in the system, so it will increase. So if turbine or work done by the fluid, then it will sudden drop. Okay, so the gauge pressure of a fluid is zero at the location where HGL intersect with the fluid. So let's say you have a reservoir and you have a pipe like this. So you, based on the previous HGL EGL curve, so you can still plot. So when the pipe is coincide with the HGL line, there the pressure will be zero. So here and also here, so the pressure will become zero, and here the pressure will be positive. Because here y is zero because it's coincide with the atmospheric pressure. But here the pressure will be not atmospheric pressure, so it will be because of the depth. So here the pressure will be positive. Uh, Down here also it will be positive, and above the HGL line it will be negative pressure. Okay, so as a summary to whatever we have studied today. So the Bernoulli's equation. So this is the Bernoulli's equation. We have seen how we derive the Bernoulli's equation. So we will get P over rho plus V square over 2 plus GZ equals to constant. Okay, so that is the Bernoulli's equation. So the first component is flow energy, the second component is kinetic energy, and the third component is potential energy. So all these three we combine, we will get a mechanical energy balance. Okay, so when you times the equation with a rho, and then you can get this equation. So it's a modification from here. So from here we can divide into three components also. Static pressure, first one is static pressure, second one is dynamic pressure, and the third one is hydrostatic pressure. Okay, all these three combined we call it as a total pressure. And the third one, so we times this equation with 1 over g, 1 over g, so we will get this equation. Okay, so from here we can divide into three components. The first component is pressure 8, the second component is velocity 8, and the third component is elevation 8. All these three combined, we will get a total 8. So all this equation and the transformations, okay, so in terms of energy, pressure, and also aid, can be used to estimate different points, different investigation, okay, in the fluid dynamics. Okay, so like we saw the total aid contributing to the EGL and also HGL line, so which will be used in our estimation, engineers use for estimating the aids or the pressures in the dam and also the bigger system. So all these three things, three equations, can be useful in various way in our fluid dynamic analysis. Okay. So as a summary, so today we have covered a lot of things, okay, related to Bernoulli's equation and fluid dynamics. So we have seen how acceleration of fluid particles, the derivation of Bernoulli's equation, the force balance across the streamline, and how we can estimate even for unsteady and compressible flow using the Bernoulli's equation. But you need to consider a lot of things. Additionally, we have seen how the Bernoulli's equation can be changed to static, dynamic, and stagnation pressure calculation. So the limitation of the use of Bernoulli's equation, and we also saw how the Bernoulli's equation can be converted into calculation of uh, aids, okay, different aids, and from the calculation of different aids, we can generate hydraulic rate line HGL and energy rate line, and how we can use this hydraulic HGL and also EGL in our daily life. And we also saw how the application of Bernoulli's equation in our daily life. So Bernoulli's equation is a very fundamental, basic, important equation in fluid, especially in fluid dynamics. Okay, so with this, I end my lecture for today. So you have understood, and in the upcoming lectures, we will see other parts of fluid dynamics and also static dynamics. So thank you so much.